Okay, so we just saw that Z was the initial ring, namely, it's the ring such that there's only one homomorphism where the domain is Z, or where sorry, there's only one homomorphism where it's the domain. There's one homomorphism out of it. In this video, we're going to ask the flip question. We want to know, is there a ring such that there's only one homomorphism into it? So that is, does there exist a ring, let's call it T for terminal, such that there is a unique homomorphism from any ring for any ring R, where T is the codomain? And the answer is, well, Z kind of worked out, right? So maybe the answer is maybe. Let's try what we know. Let's try Z. So if it was Z, we should be able to take any ring and get a well-defined homomorphism from that ring to Z. So let's try Z as T. So in particular, we could take F2, which is a ring, and if it was Z, if the terminal ring was Z, we know that there exists a unique ring hom from Z mod 2, which I'm going to denote as F2, to Z. Let's call it phi. Now, since it's a ring homomorphism, we know that phi of 1 has to be 1. Has to happen if it exists. We don't know if it exists, but if it does exist, phi of 1 has to be 1. We also know that phi should be additive. So phi of 1 bar plus 1 bar is phi of 1 bar plus phi of 1 bar is 1 plus 1 is 2, because on the right-hand side, we're adding in the integers. On the other hand, if we add inside first, 1 plus 1 in F2 is 0. And any homomorphism sends the additive identity to the additive identity. That's something that we proved. The additive identity in Z is 0. So on the one hand, we computed this and we got 2, just using properties of homomorphisms. We don't know anything about phi. We're just using properties that all homomorphisms satisfy. On the other hand, we get 0. 0 is not equal to 2, unfortunately. So phi cannot possibly exist because this is not well defined. The input 1 plus 1 gave us 2 different answers. That cannot happen. So this is not, there's no possible definition for a phi. So all this is saying, can Z be the terminal ring? No, because not only is there, well, let me back up here. There is no homomorphism at all from Z mod 2 to Z or F2 to Z. And in general, it's not hard to show. You do a similar argument. There do not exist ring homomorphisms from Z mod n to Z. They don't exist. And the reason is because 1 is eventually 0 on the left, and 1 is never eventually 0 on the right when you add them together. So they just don't exist at all. This is an important fact to know. Let me orange it. Okay, it's been oranged. Okay, so the question is, well, that didn't work. Is there something else that maybe works instead? And the answer is, well, there is actually. So let me go back and revise our answer. Yes, in fact, the 0 ring is terminal. All right, so let's go ahead and check that. So this is a theorem. So we're gonna write the 0 ring as just the ring that has 0 in it. And remember, 0 plus 0 in the 0 ring is 0. And 0 times 0 in the 0 ring is 0. And the additive and multiplicative identity in the 0 ring are both 0. So what's the theorem? For any ring R, there exists a unique ring homomorphism phi from R to 0. Proof. The codomain has one and only one element in it. The codomain has 0 in it, and that's it. So there, not only is there just one ring homomorphism, there's just one function. So we only have one choice to define phi as. We have to send everything to 0 for all R and R. And then we have to do all of our checks, right? Let's check it's a homomorphism. Well, phi of 1R needs to be 1, but phi of 1R is 0. But in the 0 ring, 0 is the multiplicative identity. The 0 ring is the only case where the multiplicative identity and the additive identity are the same. And then we have to check that it breaks up under addition. Oops, I messed that up. Let me fix that real quick. It must be that phi of R plus S is phi of R plus phi of S for all RS in R. But there's nothing to check. Everything is 0. Phi spits out 0 always. This is just 0 is 0 plus 0, which is certainly true. And then lastly, phi of R times phi of S, oops, that's not the order I usually write it. Hang on, sorry. Phi of R times S is phi of R times phi of S. Needs to be true for all R and S in R. But again, phi is only output 0, so this is just saying 0 is 0 times 0, which is certainly true. Okay. So not only does there exist a ring homomorphism, here it is, but actually phi is the only function from a set to the singleton set. There's only one function. You have to output the thing. So phi is unique. Well, let me conclude here. Phi is a homomorphism. And is the unique function. So must be the unique homomorphism. It's not even another function to check. This is the only function we have available to us to check. All right, so is there a unique guy? Yeah, it's the 0 function. And the 0 function actually is only a homomorphism when your codomain is the 0 ring. All right, cool. So we have this idea of initial, where there's only one homomorphism out, and that's Z. And this idea of terminal, when there's only one homomorphism in, that's the 0 ring. So we might ask, for example, as a question, the last thing I'll bring up in section 3.1, we might ask the following question. Well, we know that there exists a unique map from Z to 0. Because Z is initial, so there's a unique map, or because 0 is terminal, there's a unique map, and it's the 0 map. We already know what the map is. You send everything to 0. But what about the other way? How do these special guys interact with each other if we sort of reverse them? So what about that way? It turns out there's none. There are none. Sorry, I can't spell today. Why not? Well, suppose you had one. Suppose this is a ring hom. Well, then phi of 0 needs to be 0 is the additive identity. So phi of 0 needs to be 0 because 0 is additive identity. And phi of 0 has to be 1 because 0 is also the multiplicative identity. in the zero ring. So phi of 0 has to be two different integers. So phi is not well defined because a function only outputs one thing. Thus, phi is not defined, not well defined. So there's no possible homomorphism. All right, cool. So these ideas are a little bit more abstract than what we've been talking about, this idea of initial and terminal, but they're kind of the idea of initial ring is kind of natural, and that led us to considering actually the reduction modulo nmap as an example. So that was a cool example. And the idea of terminal is kind of we like to say in algebra dual to that of being initial. So if you sort of switched the location of well, you swap the role of domain and codomain, then you get the idea terminal. And this happens a lot in algebra, where if you have a concept, if there's some order, you try to swap the order, and maybe you learn something. So anyways, you know, I'm never going to ask you what the initial ring or what the terminal is, but it's a cool exploration, and it led us to some interesting behavior. In particular, we saw at least in the initial ring video how Z interacts with other rings. And let me say actually just one more thing here that I'm pretty sure I've already said, but how do we understand rings? How do you understand anything? What you do is you understand how that object, in this case, suppose it was Z or whatever your favorite ring is. One way in which you can understand it is you can understand how it interacts with other objects, right? If you want to know about something, what do you do? Well, you can try to probe it, or you can try to probe out of it. And that's what we're doing with these. That's one of the perspectives on what we're doing with these ring homomorphisms, is we're probing it or we're probing out of it.